So I have a couple of announcements after that, but since guys are still coming in, I'll continue from where we left. So I'll do a quick review of what we did last time. If you remember, we stopped here, following the steps on how to find the multipliers and how to build this LU matrices elimination. And we started with the Python code, which didn't work at that time. So these were the initial steps on how to get the zeros. And then the first x on the upper row. And we said we need to multiply the first row by a2y divided by a1 subtracted from row 2 to get a 0. Similarly, we did for the row 3. And we obtained this column of zeros. And if you continue on doing that till you reach the final shape you have here, you will have an upper triangle matrix, which is U, and you have the list of all multipliers you used. So you can put them in a column, in columns, and insert them in a matrix we call L. And we did this example on this 3 by 3 example, 1, 2, 3, 2, 5, 7, 2, 7, 8, and we've shown on the whiteboard how to get these columns of L and how to get the U. Okay, and if that was the detail, in fact, okay, and one of the things I was trying to do when we left, I was trying to share with you the way we I was trying to share with you the way we can build the code to get these this LU elimination. Okay, so I'm sharing with you now my screen for the yeah, I'm sharing with you. You guys see it? Must be working. I'm sharing with you my screen for. Yes, okay. I'm sharing with you my screen. In fact, this is the Visual Studio C++, Visual Studio platform for programming, and I've sent you a document. I'll go back to it later on. I've uploaded it yesterday on the main steps to follow to be able to install and get used to working on Python. So last time I had the problem with this loading this site package, which I installed. If you encounter this problem, well, you can look to it here in the environment part. If you see do you see my mouse, guys, pointing? Okay. Yes. If you have any problem loading the package, you will look for it here. For example, you see I left it where I stopped. I look it for the SciPy package in the Python environment. You usually have it on the Python environment on the left column, on the right column, and you can just run the command that installs the SciPy package, and then you'll be able to write your code and to make it run perfectly. So here I'm going to the mass of code. So I imported the SciPy package, and I also called the linear algebra package in the SciPy package. So I'm defining in this line A equals SciPy matrix. In fact, in SciPy now we have the possibility to load the matrix. So I entered each row of the matrix 2, 7, 8, 2, 5, 7, 1, 2, 3. And what am I doing? I'm printing out. So when I use the command print as a function, what it does, it prints whatever you want to print. So here in my case, printing my matrix A. Okay. And then I use the function LU, which belongs to linear algebra set package in the SciPy package. So when I do LU, of course, LU of A, it must give me the LU elimination or the LU factorization of A. So what it returns 3 objects. First, a matrix P, which is, I'll talk just a little bit about it in the next slide, which is a kind of permutation column matrix. I mean, it rearranges your your matrix A in a way that that is more convenient for the elimination algorithm to run. And it returns the L matrix and the U matrix. So basically, after that, I'm just printing out PLU. Okay? Everything is good? Are you okay with that, guys?
Yes.
Okay, so let me just run it here and see how this is done. So you see, these things make our life much easier. And in fact, in most of the contexts, the LU elimination takes a lot of time to do it by hand. If you have, of course, more than 3 by 3 matrix, a larger matrix than 3 by 3. And what it does, it gives you, I mean, right away here, because I'm just taking time to compile before. But here, what I can see, the display. So I'm making sure why the printing out. When I print out, I have the possibility to print on the screen, on the application screen, for the user to make sure that I'm really loading exactly the data they entered. Okay, problems entering the data might happen. 278, 257, 123. This is my matrix. So you see, it returns 3 matrix PLU, and P is just a rearrangement of the rows of A. Here, for example, when it returns an identity matrix, then it means that it didn't do any rearrangement of the matrix A. Why is that? For some reason, is that the LU elimination works better if you can be give me some attention, guys. It always gives the highest number on the first column. It considers as the first row. So you see the highest number is 2 and the first row. So that's why it put since I entered this way, 278, so it considered that this row must stay there. And it basically didn't do anything. So it returned this LU elimination, and you have a lower triangular matrix L and upper triangular matrix U, which fit the conditions of the factorization. Okay, so this is how it's done automatically, computationally speaking. And I uploaded the same file yesterday on your Blackboard. Are you okay with this? Any questions? Yes, go ahead, please. Okay, no question. So I'll stop sharing this. I'll go back to it later on. Okay. So I'll switch back to my files, and I get back to my slides. So what about the permutation? So what does the mathematician say? In fact, problems might happen when in case the first entry in the first row in the first column is 0. Okay, so basically you cannot divide by 0. You see, so this is a singular case, a case where your algorithm just doesn't make any sense. Okay, so what one can do then is to do some kind of rearrangement. Okay, so let me go back to the right slide. Okay, guys. So this is the question: what if A11 is 0? Okay, what to do if well, good codes will try to, of course, if you're writing any piece of code, you have to think about these very particular case, the case that might give you a headache or give the user headache sometimes. So good codes will choose the largest number to be the pivot. I mean, you will rearrange the rows in the fact that the row with the highest entry in the first column will be put in will be reordered and will be as considered at the new first row. Okay, and that way we obtain what we call a P matrix, which is a row permutation matrix, which rearranges the rows of A. For example, if my matrix A is given this way, 0, 1, 1, 1, 3, 7, 2, 4, 8, you see an immediate rearrangement will place where? Will we place the third row, forgive me for that, guys, as the new first row, okay? And in this case, yes, Abdulaziz.
Doctor, why we don't replace it by 137?
Because 2 is larger than 1.
So we here talk about the larger number for A11.
Yeah, good code. Yeah, because you try to put the highest value as an entry in row 1, column 1 to be the upper part. Okay, and then divide by it. Okay, so you have kind of the most scaled. You will have the most reduced form or the most scaled form of the multipliers matrix. In fact, okay. So this is a rearrangement of the rows. I'm just place it. I just exchanged what I put the first row in the second position and the third row in the first position, and automatically the second row mate went in the third position. So this is the matrix P that fits the bill here, that would make PA become the new matrix. You see it? Okay, so what it does automatically, the code, it rearranges. If you're using Python, if you're using the SciPy package, this is done automatically. You don't have to care about it. Okay? So for example, if I go back to my code and re-enter the matrix, let's see what happens. I'm pretty sure it's going to do some permutation. So you should understand that a pre-arrangement or rearrangement is done before doing the computation. Are you okay with that, guys? Okay. Well, this removes a big headache for most of us. We don't have to worry about computational aspects when the matrices are quite large. Okay. So if I go back to my code, I'll try to rearrange this matrix in a way. I'll try to re-enter this matrix in a way that maybe would be convenient to use with the code. Okay, so I'll go back to my application again. So I just are you okay, guys? You see this? So
yes.
I am entering the new rows of the new matrix, so it's 0, 1, 1 actually, and that was a singular case, a case where the first entry in the first row was a 0, and if I follow the initial description, it won't work because A11 is 0, so I cannot basically divide by 0. So now, if I enter the new matrix, make sure that it is right, just save and run. And I'm expecting a kind of a new P matrix, a rearrangement. Okay. So this is the rearrangement, guys. As you see the P matrix is not exactly as it should. It was in the first case where I didn't need any rearrangement. In fact, in the beginning, in the previous case example, P was just the I matrix. Okay. So you see now with this rearrangement, it is telling you that it places the third matrix, the third row in first position. The second row stayed in the same position, and the first row became in third position. This is how you read it. You see it? Okay? And considering this new rearrangement, you will have P times A, okay, equals LU. So this is the matrix A, and this is the matrix U corresponding. Okay, guys? So this code, I already uploaded it, after the class last time, immediately after the class last time when I started the SciPy package. Any questions on that, guys? Okay, perfect. So I'll switch back to my files. The last thing about the course content for section 3.4 was just to signal this mathematical aspect. In fact, when you are able, so this is my pointer, when you are able to write A as LU, and you are solving a system where AX equals B, it means that A inverse becomes LU inverse. Am I right? This should be LU inverse times B. Yeah? That's a typo here. There's a typo. LU inverse times B. This should be here, and this should be here. Okay? Type. And if I use the properties of matrices inversion, the LU inverse becomes U inverse L inverse, and in fact you'll be solving you'll be finding the value of X as U inverse times C. Okay? It's just the mathematical aspect of these things. So this is it, guys, for the contents of sections 1.3, 1.4. I tried as much as possible to give you the most important part. For supplementary material, you go back to the reading I already posted, okay? And you work on the problem sets I posted. Right. Now I'm sharing with you the homework I uploaded yesterday. Okay. I uploaded the homework. Are you able to see it, guys?
Yes.
Yes. Fine, right? Yes. Yes. Okay. So it was uploaded yesterday. It is due on Saturday, 11:59 p.m. Okay. So just the night before our class on Sunday. Right. It wouldn't take. Basically, I've chosen one questions from each section we covered already. So these are very easy questions, and most of them we already did them. So first question is about CR factorization. I'm giving you two matrices. I'm asking you to find the matrices C1 and C2 containing the independent columns on A1 and A2, and to factor these matrices using the C matrices you found. Okay. Then question 2 will be just asking you to perform the A times B, a matrix product, a matrix multiplication using rows by columns, and then columns by rows, as you've seen in the properties. Okay, so these are two square matrices. I'm asking you to check how much is AB, how much is BA in both ways, rows by columns and columns by rows. Right. These are very easy, guys. If you sit on it, guys, look, if you take 1 hour, one hour, half an hour, just today you'll be done with it. Right. Now, next part, LU elimination. Third question. You will need to factor these matrices, whether either using L equals LU or PA equals LU. And now we've just seen it. You have three matrices, and you need to find the LU factorization. Okay? Well, here you don't have to use the code. You can use the code for verification. Okay? But I'm asking you to do it by hand. For the A equals LU, PA equals LU. Same as for questions 1 and 2, I'm asking you to, this is a requirement, I'm asking you to do it by hand, to be able to construct these matrices by hand. Okay? Now, the next question 4 here is where you have to use a Python code. Okay? And don't worry, just after presenting the homework, I'll go through the steps to install the Visual Studio and to get used to writing a piece of code. And the main code, the most important codes that are to be used with this homework have been already uploaded. So I'm asking you to write your Python code to work on this symmetric matrix. And if you remember, last week we did this kind of factorization, the Q times lambda times Qt, in case S is symmetric. And to construct the lambda matrix, the one in the middle, we use the eigenvalues of S. And to construct the Q matrices, we use the eigenvectors of S. Okay? And you have the code to do that. Okay? And I'm just trying to make you, to force you to take this code, write your name, and hand me and run it on this new matrix and find the eigenvalues and submit the printouts. So you need, look, in bold, you add your own code print. You add your own code printout to each question and submit code with your homework. Okay. Of course, your name should be with it. As you've seen in my files, I put my name as the author. Okay? You can use my code, guys. You have the permission to use my code. Just change the name, enter the matrices, and run it to find the eigenvalues, eigenvectors, and the spectral factorization. Any question on that? Beautiful, no question. Right. Last thing is you have last question. So there are 5 questions. Each one counts for 6 points, and you have 30 questions, 30 points. 5 times 6 is 6 times 5 is 30. Okay. Each question counts for 6 points. The last one is about fundamental subsets. So I'm giving you a first matrix A. I'm asking you to find the column space and the null space. And similarly for the next matrix B, I'm asking you to find the row space and the left null space. Okay? And that's it for the home. Any question on this, Shabab? How to hand it to me? How to change? I added on the top of the cover page, you see you have my email, my KFUPM email. Send me your work, either scan it, camera scan it, or the code file, my email. You have it on the top. Before 11:59 p.m. Saturday. Shabab. Okay? So this is our... Yes, Abdulaziz, go ahead.
I have a problem with the Visual Studio, actually.
We can talk about it later on, for particular questions, Abdulaziz. Okay? But this allows me, Abdulaziz, to introduce the document I uploaded last time. Okay. Now, for some of you, maybe they're not used to Python programming or C++ programming using a platform. Okay, so this is how to get started. I prepared this short document, very short document, to get you started with it, and you have to get started with it. Okay, if you're planning, if you chose your concentration, chose these kind of courses, data science courses, to enter a track where your career is built on data science and machine learning and deep learning and stuff like this, you have to get used to programming. Okay, and this is a thing that is a bonus on your CV. It's not only a bonus, this is a major requirement. Nobody would hire you if you don't know how to code. Even if you pretend that you can do data science, nobody is doing theoretical mathematics in the industry. You have to be able to use computers to use your own programming skills. So how to get started with Math405 Python programming? First of all, follow this link. If you follow the link on the deck, you have the Microsoft link to install the Visual Studio. Okay? Then you follow these steps with the hyperlinks that are there. You have the installation of the Python package, how to get to create your first Python project, okay? And how to get started with writing and running code. You have some couple of examples, okay? And honestly, guys, these are the steps I followed a couple of weeks ago to do this. Okay? Even though I have more than 20 years of experience running in C and C++. Now, the next question, why do I have problems running the code posted on the Blackboard? Even if you download my code, which is on the Blackboard, you will have problems running it, even if you did the installation perfectly on your computer. Because the package we are calling here, NumPy, SciPy, are not pre-installed. And remember, as I talked before, this is what happened last time. Okay? So you check, you look for the on the Python environments, you look for the package, for example, NumPy or SciPy, and you run the command to install, and you'll be done with it. Okay? Inshallah, you'll be done with it for every package you upload. You'll be done with it for the whole semester. Okay? Is it clear for everyone?
Yes.
Yeah. So, any question?
Doctor, how we can install the packages?
You can open this document. How you install the package? Okay. I'll share with you the application screen. Okay. You see it? Are you seeing my application screen? Yeah, it is. We see the Python environment here, this column. The Python environment column. Here, when you can choose the possibility, you have the possibility to look for packages. For example, I can choose for NumPy. NumPy, to me, it was already on. Okay? And I used NumPy last time. In fact, when I did the spectral factorization, you find NumPy, you just run the command to install it, and immediately you see that is when you run it, it is installing download the package and installing it. Okay, Abdulaziz?
It's not like this appearing in my program.
You mean you don't have the column like this?
I have Python environment, but it's not listing the packages like this, like you have.
You have to look for it. You have to look for it here. Okay. See, you have a kind of a browsing window where you can look for packages. You should have it. Have it right now. Okay, you see SciPy appears down. You have the possibility to see all the available packages if you wish. Right. So this is about the Visual Studio part. Hopefully, guys, if you have personal questions, you can send me an email, and hopefully, inshallah, I'll be able to provide you at least with some hints on technical support and advise on which links you should follow to get answers to your questions. Okay, inshallah, and we'll get used to it. You see, a couple of hours, couple of days, guys, will get used to Python, inshallah. Now, I'll switch back to my files and prepare for you the course material for today. So today we start section, inshallah, section 1.5 about orthogonal matrices. Okay, and this basically covers 1.5 section in the text. So let's go. I'll talk in this presentation about orthogonality, singular vectors, and projection. If you're not that good in linear algebra, even if you skip most of the concept of linear algebra, you'll be able to understand most of the parts of it, because this is basic. I mean, let's say mathematics from the last years of secondary school, okay, or the prep year. Type. What is orthogonality? Orthogonality in geometry, guys, or usually in mathematics, means two objects that are perpendicular are said to be orthogonal, right? In the mathematical way, we always try to check that by doing a product. For example, if you have two vectors, x and y, their product should be equal to 0. Okay? So if you do the product x transposed by y, you will have the sum of the product of each element of each element, corresponding element 1 by 1, 2 by 2, n by n should be equal to 0. Well, the notion here now is extended beyond the notion of angle. Orthogonality extends perpendicularity beyond the notion of angle having a 90 degrees. In a subspace, two vectors are said to be orthogonal if their product is equal to 0. And what do we mean by orthonormal basis? Orthonormal basis means a basis, I mean a set, a minimal sized set of vectors that is able to generate a whole subspace, but the vectors have unit norms. So these are what we call unit vectors. For example, in the 3D Cartesian plan, or the Cartesian space, sorry for that, ijk are usually considered to be unit vectors, and the product of each pair is 0. Now we extend also this notion to what we call orthonormal columns. For example, we'll talk about what we consider to be very thin columns, such that qt times q equals I. And this gives birth to what we call orthogonal matrices, which are square matrices with orthonormal curves, colors. So let's get into that. For example, if you consider the vectors, which are given here, x and y, you can see that vector 1, 2, 2 multiplied by vector 2 minus 1. Of course, when you put x transpose, you get a 0. You'll get 2 plus 2 minus 4 equals 0. So the two vectors define the two sides, in fact, of a right triangle, if you think of it in a three-dimensional representation. They should be orthogonal. Okay? So, and why am I writing the hypotenuse could be given by x minus y? Well, for sure, if you consider, for example, that this is x and this is y, okay? So the hypotenuse could be obtained when you go from that point, from the point A to point B. You can do minus x, so the opposite direction of x, minus x plus y should give you the hypotenuse, if you wish. Okay, got it? So in R cube, the usual vectors I, j, and k, divided by 1, 0, 0, 0, 1, 0, 0, 0, 1, define what we call an orthonormal basis. Why is that? Because their norms are equal to 1. Okay. Now we talk about also what is very funny is that we can define what we call the Hadamard matrices. Well, the Hadamard matrices contain what we call orthogonal basis in R squared, R4, or R8. For example, if you consider this first one in R2, you see the product of the two columns is equal to 0. Okay? So this constitutes the columns and the first Hadamard matrix H2 here. They do form what we call an orthogonal basis in R2. Now in R4, you see the four columns here are different, and if you take the product of each pair, it would give you also a 0. So they do form an orthogonal basis in R4, and you can also use this H4, this whole matrix, you can call it H4, and you can place it in this way. You can build what we call an HA, so an Hadamard matrix with size 8, and place it this way, it builds also an orthogonal basis in R8. Okay, so this is just for your information. Now, what about orthogonality for subspace, columns, and matrices? So if you consider a given matrix A, well, what we can be sure of is that row space. What is the row space? The row space is the space generated, all the combination of the independent rows of, okay, what we call CAT. What I'm sure of is that it is orthogonal to the null space of A. Why is that? Because for every x in N of A, for every x in the null space of A, I'm pretty sure that I'll have AX equals 0, sir. And this defines, in fact, the belonging or the inclusion in A, and this defines also orthogonality, because AX equals 0. So, in fact, every row of A is orthogonal to X. You got it? Every row of A is orthogonal to X. So the whole row space is orthogonal to X. Or in other words, the row space of A is the set of all vectors orthogonal to X. Got it? The column space at the same time of A is orthogonal to the left null space of, or to the null space of AT, or the left null space of A. Of course, when you are talking about the left null space, it's the set of all y's that satisfy ATY equals 0. Okay? So in a way, what can I say? In fact, you see there is a 90 degrees angle between the null space and the row space, and the column space and the null space of AT, or the left null space. These are orthogonal subspaces, as you can see. Okay, just to give you, I mean,
a global idea of what is going on in geometry. These are perpendicular or orthogonal subspaces generated from matrix A. Okay? طيب. Why is that happening? Why is that important to be seen in data science? Maybe any one of you guys can ask the question, why do we have to see that? Well, guess what? If we are able to generate orthogonal matrix spanning matrix, life is wonderful, because I'm pretty sure that the multiplication will give us a 0. So computationally speaking, it's less demanding. Well, this is what we'll be trying to do when we use what we call singular vector decomposition. SVD stands, guys, as an abbreviation for singular vector decomposition. It's the most important theorem in data science. Okay? Well, what it does, it finds orthonormal basis. We've just seen what we mean by orthonormal. Orthonormal basis means a set of vectors that is able to generate my whole subspace, and each vector has a unit norm. So singular vector decomposition finds orthonormal basis V1 to VR for the row space, and U1 to UR for the space. Okay? The special basis from SVD have a property that each pair V and U is connected by A. So you'll have the following property, that AV1 is equal to sigma 1 U1. This is the link between V1 and U1. V1 and U1. AV2 equals sigma 2 U2. Sigma here, all the sigmas are kind of multiplied, or real numbers. AVR equals sigma RU. So from the base of the SVD, multiplying by A takes an orthogonal basis of V to an orthogonal basis of A. So when you multiply V by the matrix A, what happens? You will shift to the other basis. You shift to the other subspace. So this is to give you a global idea about what is done. Okay? Now, for example, let's talk about these columns where that satisfy the property that QT times Q equals I. So for example, if we take the 3×1 column Q1, which is given by 1/3 of 2, 2 minus 1. What you could check is that QT times Q, in all the cases here, is equal to I. Okay? QT times Q, in all cases, is equal to I. Okay? So we've been growing from 3×1 to 3×2 till the last one to 3×3. And in each one of these matrices, we have Q equals I. And more than this, if you can focus with me just for a couple of minutes, Shabab, we can generate what we call a projection matrix, which is called P. And what is particular to the projection matrix is that P is equal to QT. It's a kind of matrix that satisfies the fact that P squared is P. Why is that? Because if you place P against P, it will give you QT Q times QTQ. Am I right? Now in the middle, this guy is nothing but I, so at the end you end up just QTQ. So P times P, or P squared is just P. And the equation P squared equals P sigma is what we call a projection matrix. What it does, once multiplied by a vector B, it projects a vector into the column space of P. Let's see an application. For example, if you consider this vector 3, 3, you see it here. 3, 3 is here. Okay? This is it. If you multiply by the matrix P1 generated from Q1, where 1 was given as 1/3 of 2, 2, -1, you will have the following. First of all, we define P1 as Q1 times QT. So P1B would be equal to this is the whole matrix T1. Huh? This is T1. Doing Q1 times QT. When you multiply it by 333, you obtain two things. The matrix is B in two parts. First of all, the projection on the row space of B. Okay, this is the projection. You see it? So B, which was here, 333. Here is it. هذا هو 333. هذا هو الفيكتور يا شباب. شايفينه اللي فوق هذا الهايبوتنس. Okay. Projected on the line 2, 2 minus 1. It gives you this part. هذا T1B. And the remaining part is that the error of projection. We call it the error of projection. It is given by I minus T1B. Okay. Now the question is why we do mathematically want to do a projection. Okay. For example, in visual recognition, you have a 3D picture or 3D scan of an object, but if you want to represent it correctly, you always tend to do a 2D scaling, 2D projection of that face. Okay? Even to be able to represent it on a software, when you do rotation, on every side you have a kind of 2D representation. Okay? Of course, when you do a projection, you have a loss information, and the loss information here in image recognition or visual recognition is interpreted by the error. You see it? Okay? So mathematically speaking, when you have kind of a colored matrix on a 3D shape, okay? If you want to project it on subspace, on some space, you do a multiplication, but you have a loss of information. Okay? And this is what you obtain. You obtain 2 minus 1, for example, here when you project 333 on the line given by Q1. Okay? Any question on that, Shabab? So this is just a summary of the first part of section 1.5. The most important ideas are here. Now, do you guys have any question? Okay, so look, now my question here, I'll be making myself available on Thursday for an office hour. So today is Tuesday. So I'll be available for an office hour Thursday from 12 to 1 p.m. Is it okay for you guys? For the office hour. Some of you, one or two guys asked already for office hours. You guys hear me? That's the same. That's the same.
Sir, when you upload the downloaded video or the recorded video?
The recorded videos? I think if you go to Blackboard, let's go together. Look, let's go together. If you go to the Blackboard, are you with me? Yes. I'll share with you the. I'll share with you my. Wait. You have the session, and you have on the left space, on the left part, you have to see. You can see the recorded video. Are you with me?
Oh, yeah. I just noticed. I didn't. Sorry.
I'll show it to everyone. No, that's perfect. I'll show it to everyone. Because many have been asked about it. So I'll share the application screen. So this is my Blackboard. Are you able to see it? Or not yet?
Can't see. Not yet.
Okay. So I'll share with you. Okay, let me try to share it with you, okay? Are you able to see it now?
Yes.
Okay, you see, I'm pointing there, and you see the recordings. You see it there? You click on recordings, you have all recorded sessions.
Doctor, it's hidden from us. The online lecture often it's hidden.
So you don't have the recordings?
No, I can't see it.
No,
Yeah, I have it.
online
I can see it.
Anyone has it?
Yes, me, I have it.
So it might be that there might be, if you are now, right now on your mobile phone, it might not appear because the mobile phones, most of them, they don't support the full possibilities you have on a laptop or a desktop browser. Okay?
Sorry, sir, but 5 seconds ago it was appeared in me. Now it's not.
So can you reload it, please? It should work. So
Yeah, I
think
it should be there.
Collaborator. It's not on the sidebar.
On the sidebar, you have a menu.
It's not in our sidebar.
So I'll go back.
Yes,
You have
we
it
can't
here?
find it at the sidebar, Doctor.
Okay. So I'll send you the links anyways, but I just wanted to tell you that it should be there automatically. Some of you they have it, some not, but I'll send you the links, okay? Anyways, let me take the attendance quickly. I'll stop sharing this with you. Yes, any questions, Shabab?
No, thank you.
Doctor, on Thursday I have a class from 12 to 1.
12 to 1, you can just, if you finish at 1, you can just let me know if you, who's talking, Hussein?
Abdulaziz.
Abdulaziz. Okay, so I'll be there from 1 to 1:30, just as we communicated together yesterday. Please let me know if you have any question, okay?
Okay.
طيب, Mohammed Abdurrahman is here.
Yes.
Abdulaziz Sambol.
Yes, Doctor, here.
Sultan Aboudi. Sultan. Khalid al-Badia.
Yes.
Hassan al-Bin Saad. Hassan bin Saad.
Yes.
عبد الإله فرج.
Yes.
فارس الحسن.
Yes.
عبد الرحمن الحسين موجود؟
Yes, yes, yeah.
محمد جالود.
Yes, I'm here.
عبد الله العريني. نعم.
Yes.
ثامر العتيبي.
Yes, Doctor, I'm here.
اهلا وسهلا. عبد العزيز الراشد.
Yes.
فراس الرميخاني.
Yes.
عبد الله الرقيعي.
Yes.
حاتم الرويس.
Yes.
حاتم الرويس. يس. نواف الشهري.
Yes, Nawaf Sheri.
فيصل السبيعي.
Yes, Sasbay.
فيصل موجود.
Yes,
اهلا
yes.
وسهلا. عبد العزيز موجود. زياد بحلس.
Yes.
بنتان موجود.
Yes, موجود دكتور.
عبد الله بارون.
Yes. موجود.
خالد السودان. خالد. ركان كعكي. محمد السليم.
Yes.
طيب I have absent يعني سلطان العبودي and خالد باسودان. سلطان العبودي خالد باسودان. Okay. طيب. Okay guys. Thank you very much for listening. So see you next time. I uploaded all the material and enjoy. If you have any questions, send it to me by email or we have office hour inshallah on Thursday, inshallah from 12 to 1. Okay guys? Yalla. See you. Assalamu alaikum.